Hi, class. This is the Zoom session for the Conservation of Momentum Lab. Okay, so this is the next lab in the series of labs. You know, we've gone from Newton's laws, talked about the conservation of energy. So that is our, that forms our four major laws of physics that actually underlie the theory of mechanics. Now, we're going to talk about another conservation principle that is very widely used in physics. That's called the conservation of momentum. So first of all, the best way to really understand anything in this class is really listen to the lecture. All right, so this is going to be kind of more of a mini version of what's in the lecture anyway. So first of all, what is momentum? Well, if an object of mass m has a velocity v, then it possesses a momentum p equals mass times velocity, mv. Now, the velocity is a vector. The mass is a scalar. A scalar times a vector is a vector. So P is, I don't know why we always use the letter P, little lowercase p for momentum, but we do in the physics community. But P is a vector. Now, the question you always want to ask yourself is, what's so important about momentum? Why do I want to define this? So what if I can multiply these mass times velocity together? What is the importance? Just like you should ask yourself the question, what's the importance of energy? Well, energy is conserved, right? Well, one of the things we're going to find out today is momentum is conserved. And of course, you use a conservation principle in order to be able to solve physics problems. All right, so it's a couple of major reasons why momentum is so important. All right, first of all, momentum was understood first by Sir Isaac Newton. And Newton actually understood momentum to be the more natural physical parameter of the universe. Momentum is more natural than, say, velocity, mass, or any of the kinematic variables. Momentum is much more natural. And so Newton understood this. Newton had incredible physical intuition. All right, and in fact, Newton's second law is written in terms of momentum. All right, so in the Principia, the great physics book written by Isaac Newton, in the Principia, remember, the Principia was the great book that Newton worked 18 months on, and he gave us the laws of physics. He gave us pretty much went from nothing to everything in this book. We understood for the first time ever the concept of a law of physics, right? But in the Principia, Newton wrote the second law in terms of momentum. And what is that? Well, the left side looks the same. Sum of all forces. Summing all forces on an object or a system, if you will. And instead of mass times acceleration, like we're used to, Newton wrote that it's the time rate of change of the momentum. In reality, I would use calculus to do this. I'd have little d's here instead. but wanting instantaneous momentum, what would I say? Well, I would really want to say that this is, in reality, I would say that this is the sum of all forces is the limits as delta t approaches 0 of delta p over delta t, which we know in calculus is the first time derivative. So I put little d's here. But I want the instantaneous time rate of change of the momentum. Little d's here instead of deltas, right? But we're not doing calculus here particularly. You have a question, Shadar?
Yes, I do. It's not related to this, but it's a kind of serious question.
So we're recording right now. Just let you know. Just
it's about the lab.
oh, okay, fine.
A lab. So
Okay.
on the conservation of mechanical energy, the website, it's not working.
Yeah, I'm going to talk a little bit about that tonight.
Okay.
So I think as of December 31st, Real Player, I guess, is no longer supported by, I'm not really sure what, Windows or what, but Real Player. So some of the labs were written according to Real Player. Now there's a workaround. If you look carefully, you'll see an HTML link, a corresponding HTML version.
Yeah.
So I'm going to cover that tonight. Now,
okay.
The problem you might find, is that the HTML version of lab is similar but not the same as the Real Player version of lab.
Yeah, it looks very different, so I got confused.
Okay, that's mechanical energy. All right. Interesting. I actually ran through the lab. In class. I ran through it in the session.
Yeah, I watched the video, but the one you use in the video is very compared to what's available, it's very different. So it's hard to correlate them together.
Well, let's you know what we can do is toward the end of this session.
Okay.
Let me take a look at that.
Okay.
I mean, we're recording everything here anyway, and I don't think this is going to be a very long session. So, I mean, the lab's pretty short here, and then we can see. I can poke around and see what's going on for mechanical energy lab. Maybe something changed.
Okay.
All right. So anyway, let's see here. So we have Newton's second law written in terms of momentum. All right. Now, you might ask the question: is this the same thing as? I mean, you told me Newton's second law was mass times acceleration over here. This doesn't exactly look the same. What is it the same? And the answer to that is it is, with a caveat. All right. And so let's take a look at. So again, let's take a look at. I'm going to rewrite. Let me get rid of these words and kind of do a little real estate shuffling here. So let's rewrite the momentum. Let's kind of see what that caveat is. All right. So summation. So again, Newton's second law, as written by Newton himself, is the summation of all forces is the time rate of change of momentum. All right. Now, time rate of change of momentum. Well, what is momentum again? Well, again, momentum is defined as mass times velocity. So I'll substitute that in there. So Newton's second law becomes the summation of all forces is the time rate of change of mass times velocity. Now, we're going to do something a little bit different here. We're going to make the assumption that I'm going to be very, very general. I'm going to assume that mass can possibly be a function of time. We know velocity invariably is, because velocity is defined as a time rate of change of the position. So in the whole scheme of mechanics, velocity is inherently related to time. But let's just kind of imagine for a moment that I can write that the mass is inherently a function of time, and the velocity is inherently, I mean, we know it's a function. I mean, I'm being very deliberate here. Now, what you're trying to do is take a time rate of change of a product. Let's say a product, two functions multiplied together. In calculus, you have what is called a product rule. So again, what a product rule says, I'll try to write it in the deltas. product rule basically says that if you have, let's just say that h of t is a function of two other, is equal to a product of two other functions, say f of t times g of t. And I want to take the time rate of change of h of t with respect to the independent variable. Again, my independent variable this time is t, but it doesn't have to be, whatever the independent variable is. What you do with the product rule is you take turns applying it to only one of the functions at a time. So I'm going to say, okay, it's f's turn. All right. And so I'm going to say, take delta f of t with respect to t. I'm only going to apply the time rate of change operation on f, and I'm going to leave g by itself. Leave it alone. Okay, it was f's turn. Now it's g's turn. So now I'm going to leave f alone. I'm going to multiply, and now the operator goes on g. It's g's turn in the barrel. All right. And if I had three functions, let's say h was f g times j, I'd have three terms. I'd have the term where it would be f's turn, the term where it's g's turn, and I'd have a third term where I'd leave f and g alone, and I would multiply it. I would do the operation on j. And that's how the product rule works. So in calculus, if you were to take differential calculus, you would see the product rule written in terms of what are called time derivatives. All right, a derivative is the way you say is slope in calculus. It's the instantaneous slope, and calculus is all about doing derivatives. I mean, at least calculus 1 is differential calculus, right? But anyway, I'm using this situation here. So now let's take this product rule and go back to what we're talking about here, Newton's second law. So we have this operation, again, it's two functions. My functions are not f and g, my function are now m and v. All right, and of course my v is actually a vector, but it doesn't matter. It's still time dependent. All right, so it's m's turn. Summation of all forces, and the left side doesn't change at all. It's m's turn, so delta m of t with respect to t. Leave the velocity alone. And I'm just being explicit, they're a function of time. And then plus, now it's the velocity's turn. So I'm going to leave m alone. And now I'm going to take the operation and apply it to the velocity. Okay, well, that delta v with respect to t, that definitely is reminiscent. I know what that is. I know that's the acceleration. So I can actually write the acceleration as delta v of t with respect to t. I recognize that. All right, so I recognize that, so I can actually put that there. So I'm going to continue up here. So what do I have now for Newton's second law? I have the summation of all forces is the time rate of change of the mass. Leave the velocity alone. Plus ma. All right, now, let's see here. Summation of all forces is mass times acceleration. That's what we learned a couple of chapters ago. But this is a little different now. Now, how do I get the form from a couple of chapters ago? Well, I do that by trying to, that term would have to go to 0 somehow. And it would go to 0 if, delta m with respect to t would go to 0. Why? When? If the mass was a constant. So if the mass function is constant, if the mass of the system is a constant, well, the time rate of change of a constant, well, it never changes. It's a constant. Then, so delta m with respect to t would be 0. Then we have what we had before. Summation of all forces is mass times acceleration. So what you learned back in a few chapters ago is Newton's second law. If the mass of the system is a constant. If the mass of the system is not a constant, then you have to use this more complicated version. Now, when might the mass of a system? Is that kind of a oddball concept that the mass of a system would not be constant? Well, no. There are good examples where the mass of the system is not a constant. One such example would be a rocket ship. If you look at a rocket ship, almost all the mass, you have this little capsule that's supposed to go out in space, almost all the mass is fuel. So examples of systems where the mass depends on time, or the mass is a function of time. You're not too oddball. What comes to mind would be a rocket. You look at the rocket sitting on Cape Canaveral, for instance, majority of its weight, the majority of its mass is all fuel. The escape velocity of anything from the Earth is 11.3 kilometers per second. Means you have to get anything, a capsule, whatever, up at 11.3 kilometers per second to escape the Earth. So there's a lot of fuel required to do that. The majority of what's on the rocket sitting on the tarmac, the majority is its fuel. Another example is a missile. A missile eats itself up to deliver a warhead. Literally a missile, if you look at a missile, you have the warhead up here. The missile literally will eat through itself. It'll propel itself, but it literally eats itself in order to deliver the warhead. So it's on a suicide mission by design. And then another example, what you might not think about, is your car. The car has a fairly small function, but you think about it, I don't know about your car, but my car holds about 20 gallons of gasoline. Now I do my own lawn, so I know I have a gas container that holds about 2 gallons, and I can tell you, I mean, I lift that. It's a significant weight. There's a lot of mass in that gasoline. Now you multiply that by 10, that's a lot of mass of gasoline that goes in your car, and that gets burned up, and your car is almost on empty, and you have to go back to the gas station and fill up again. And of course, that mass of gasoline is small compared to the mass of the car, but still it's a significant mass. And you're burning through that as you drive around. So yes, there is a small MFT function for the burn rate of your gasoline. Even though for a short distance, you could say, yeah, if it goes MA. But if you're considering, really a longer duration, you're going to have to consider like the burn rate, depending on how precise you want to be. You'd have to consider the burn rate of the gasoline in the car. All right. So again, it's not so far-fetched. And the only way to obtain this knowledge is to understand that Newton's second law really depends on the time rate of change of momentum. That's the true form of it. Okay, now let's move on. So, looking at the lectures again, we also talked about something called impulse. Now, you go back to Newton's second law, you write again, we'll just say average force. We'll say net force. Again, sum of all forces is really all together. It's a sum of vectors, and you get a net vector. Okay, I'm just going to kind of write things in just one dimension for right now. And Well, what's Newton's second law say again? Well, it's going to be delta T with respect to T. Well, let's cross multiply, and I'm going to write that delta P. Oh, but now vector hats off. Is F net average, we'll say, delta T. Now, we're considering a situation. So we are considering a situation where there is a sudden change in momentum. Where delta T is small. Okay, so an example would be the change in momentum of a baseball. When hit by a bat. Now you look into Major League Baseball, you know, you gotta have a pitcher throwing, say, 95 miles per hour. The hitter has very high velocity of his bat speed, or they call it bat speed. And that ball goes from, in a split second, from 95 miles an hour going toward home plate to like 100 miles per hour going out into the field. Very fast, boom. You know, this situation, when you see a situation like this side of the equation is called the impulse. A very large force, and it's hard to characterize this force. That's why you call it kind of an F net average, put us over bar here, multiplied by a very small amount of time. That's called the impulse. All right, and so I need to use the concept of an impulse to get to the conservation of momentum, which is what this lab's about. All right, so let's imagine this for a moment and say, okay, well, and again, this delta P is a change in momentum. Mass times velocity of the baseball is going one way, all of a sudden, boom, the mass times velocity of the baseball is going the other way. All right, so now let's talk about, I'm gonna drive the conservation of energy. I'm sorry, the conservation of momentum. And I'm gonna consider a very simple example. You can imagine two billiard balls striking each other. All right, so let's imagine I have two balls. I have a mass m1 going at initial velocity v1I. And I'm just going to leave off the vector hat for the moment. I have another ball, m2, and it's going at initial velocity v2I. I stands for initial. Okay, so initial. Now, these two balls are going to strike each other, and they're going to go the other way. So bam, they hit each other. Or I guess in pool, it's clack, whatever that sound is. And then they are, here you got M2 going off at V2F. F, as usual, stands for final. And M1, no, we're assuming the masses, of course, stay the same. In collisions, that's not always true. B1F. All right, so that's the situation. Now, when they collide, they are for a very brief moment having this impulse relationship. So let's kind of imagine that here is the moment that they collide. All right, and they collide, and at the moment of collision, ball one experiences force F1, which is the force on ball one due to ball two. All right. Ball two experiences a force F2, which is the force on ball two due to ball one. Okay, so at the collision, ball one experiences force F1, which is a force on ball one due to ball two. Ball two experiences the force F2, which is a force on ball two due to ball one. All right, and then you can think of this M1 as having a momentum, say P1I. I'll leave the hats on. P1I here, this momentum is P2I, and finally, this momentum is P1F. This momentum is P2F, right? And you just get there by multiplying the mass times velocity together. All right, so each one of these is experiencing change of momentum, each ball, over a short period of time. It's kind of what I did in words, is kind of write it on in math. All right, so let's look at ball one and ball two. So again, I want to look at the time of collision. At the time of collision, at the moment of collision, what's happening? You got ball one, ball two. All right. So ball one is going to experience an impulse. So it's going to say, okay, well, I have a delta P1. Why? Because I experience this very short time, this short impulse, this short duration impulse. So I experience this F1, which is like an average force that ball one felt over a time delta T. So ball one certainly experienced an impulse, a change of momentum. It went from P1I to P1F. No doubt about that. Ball two also experienced a change, an impulse equation. Ball two had delta P2. It experienced force F2 for the same duration of time, delta T. All right, so each one of these balls has its impulse equation. Now, here's where we relate the two. According to Newton's third law, from Newton's third law, F1 and F2 are an action-reaction couple. Which means that one is the opposite of the other. So F1 is negative F2. They are equal and opposite, according to Newton's third law. I push on you, you push on me with equal and opposite force. So what I can say now is I can rewrite these equations. I mean, I'll leave ball one's equation alone. Delta P1 is F1 delta T. But ball two, instead of F2, I'll put negative F1. So now delta P2 is negative F1 delta T. Okay, I can say that because of Newton's third law. And now what I can do is I can solve both equations for F delta T. So F1 delta T. So F1 delta T. Okay, they're common. Delta T is the same, and F1 is the same. Well, that's equal to delta P1, but that's also equal to negative delta P2. All right, so I can eliminate F1 delta T. Now what do I have? Okay, I'm talking about the moment of collision. What I have now is simply delta P1 is negative delta P2. Put the delta P2 on the other side. I have delta P1 plus delta P2 equals 0. And let's see here. What's delta P1? Oh, that's right. That's P1F minus P1I. What's delta P2? P2F minus P2I equals 0. I can rearrange, and what I get is P1I plus P2I is equal to P1F plus P2F. What that says is if I add momentum, the total momentum of my system will remain constant. They always will add up to the same momentum. This is called the conservation of momentum. So I'll just write it, I'll erase this. So we have derived the conservation of momentum. Okay, let's write it in. What did I just show you? What I said is the total momentum of all objects in a system at time t1 is the same at any later time t2. Now here's a caveat. Provided that the system is isolated. Now, what does that mean? An isolated system is one where the net external force on it is 0. I didn't say there was no force on it, but whatever forces, whatever external forces are on that system, they all sum up, they all balance out to 0. As long as I have this isolated system, momentum conservation will be true. Now, here's the beauty about momentum conservation. There's pluses, you know, there's takeaways, there's trade-offs to everything in life. All right. So, you know, the conservation of momentum. Well, first of all, let me kind of back up a moment here. So you might say to yourself, or you might be thinking, wait a minute. You told me earlier, and actually a few minutes ago, that there were only 4 laws of physics that are the basis of mechanics. Newton's three laws of motion and conservation of energy. What about the conservation of momentum? Isn't that a law of physics? And the answer is technically no. And why is that? Well, the conservation of momentum, so let's go back to what the definition of a law of physics is. A law of physics going back to the first day is a behavior of the universe that does not have a more primary cause. It is the primary cause. So, if you ask the why questions, like let's say you're talking to an 8-year-old, they're asking a bunch of why questions and why this, why that, why this? Well, it's because of that. Why that? And because, and you go on and on. Eventually, it leads to a law of physics. Maybe your next question, the next question this kid will ask you is, why is Newton's second law? And the answer is nobody knows. It just is. It is a behavior of the universe. We had to discover it. We don't have the second law doesn't have to be true. It just is one of the fundamental behaviors of the universe. That's where physics ends. If you're a religious person, you can say it's true because God made it so. But really, it's where physics ends. All right. However, I can say that for Newton's three laws of motion and the conservation of energy. But if I were to ask, why the conservation of momentum? Well, if you go back to my derivation, it is due to Newton's third law. I had to use Newton's third law. And I don't derive a law of physics. The fact that I derived the conservation of momentum should tell you right there, you only derive something based upon first principles. So you don't derive a law of physics. I never derived Newton's second law. I handed you Newton's second law. I said, this is Newton's second law. I derived the conservation of momentum. You don't derive a law of physics. All right. So first of all, why is the conservation of momentum? It's due to Newton's third law. Now, if you were to go on and say, why Newton's third law? Nobody knows. All right. So the conservation of momentum doesn't have the same foundation or fundamental standing as does the conservation of energy, or as does Newton's three laws of motion. However, everything in life's a trade-off. The conservation of momentum is generally much more useful. If you can make an isolated system, which is a very, very easy thing to do, you can apply the conservation of momentum and do physics problems. If we're meeting face to face in the lab, a lot of the lab equipment at our school is not very good. And you're not going to get a lot of, generally speaking, like Professor Bench kind of tells me, he says, you're good if you can get plus or minus 5% with the quality of the equipment. We're not using the equipment you're going to use at NIST. You just don't have that. We don't have that kind of funding at TCC, right? So you're going to, but no matter what the equipment we have, the conservation of momentum is usually a lab that you can get really good precision, better than plus or minus 5%, because it's a very easy lab to do, and it's very applicable. There's not a lot of room for error. There's not a lot of, like, unlike the conservation of energy, you can say, well, I have mechanical energy. I have an elastic collision. An elastic collision is where energy is conserved. Oftentimes people will give it as an example of that, two pool balls colliding. A good example of an elastic collision are two pool balls. But the thing about it is, if I were to walk into a bar, or you're to walk into a bar, and you walk in and say there's a pool table and people are playing, you would hear the characteristic clack. Or if I played a sound bite for you, you'd hear that. The fact that you can hear that clack means that there is sound energy being given off. So it is not truly an elastic collision because you hear sound energy. So there's at least some small amount of energy being given off. We assume for all practical circumstances that the collision is elastic, but generally there's no such thing. So generally, you really can never, at least in mechanics, you really can never apply the conservation of energy perfectly. You can almost always apply the conservation of momentum. All right, and so again, there's trade-offs to everything. So yeah, the conservation of momentum is more of a, call it a blue collar principle. It's not at the level, pure level of, say, a law of physics. But the reality is, if you look at, conservation of energy, conservation of momentum, you kind of can make a comparison. Almost never can be applied for energy. Almost always can be applied for momentum. There are some good things about energy. Energy is a scalar. For energy, I can just add up numbers. So energy is a scalar. Momentum is a vector. I got to go into components. Conservation of momentum applies equally in all two or three components. We're doing things in one dimension here, but it's a vector. Momentum is harder to apply. You've done momentum problems already in this class. We've already had an exam on. I mean, it's not too hard for momentum to get gnarly, right? Especially you go to multiple dimensions. So momentum is a vector. So it gets messy. And of course, energy, there's many types of energy. Kinetic energy, potential energy, work, radiant energy, thermal energy, so on and so forth, right? Momentum is just momentum. You don't have some different types of momentum. You just have momentum. All right. So there's a plus or minus on anything. I mean, this is truly a law of physics. Conservation of energy, conservation of momentum is not. And hence, like I said, I can derive it. Now, in this class, in this lab, we're just gonna go and do one dimension. So that's all I have to say theory-wise. Again, it's kind of the short version of what you really learn in the lecture. But again, I want to kind of remind you, since we're kind of doing the labs a few weeks after we actually cover the official material. All right, and so I just want to remind you of that. All right, so I'm going to go to the lab, and Shadera had a question earlier about some of the labs having a hard time working, and you would find out doing this lab, you'd have some difficulty. So let's kind of start off, and then and I'm gonna kind of walk you through even firing up this lab. So any question about the theory before I get going?
I'm good.
Shadera, you good?
Yes, sir.
All right, awesome. All right, so here we go. I'm going to share my screen. Well, you know what I'm gonna do? I'm going to click right now. You don't see anything yet. I'm just going to click on the link that's in the Word document. So that still is okay. I should have probably done that earlier, but I'm going to click on it now. Hopefully something's actually happening. All right, yeah, I see the little spinning wheel here. So give me a moment, and then once I start seeing something, I'll share my screen. Let's kind of walk through this difficulty together. So the lab's going to look different a little bit, but for the most part, it's for the most part, it's the same. And then Shadera said that earlier on that the energy conservation lab had an issue. So I'm going to go look into. Right when we get done with this, it's not a very long lab. When we get done with this, I'll investigate the energy conservation. It actually worked. Like I said, I worked that lab just like I did this one, so I'm a little bit surprised by that. All right, is it coming up? Sorry, I should have. All right, here we go. Should have did this click earlier. All right, it's still firing up, believe it or not. For some reason, Zoom really slows down everything on my computer. I don't know why that is. All right. All right, so let me share my screen now. I'll show you some ugly stuff here in a second. All right, so when you click that link, you're gonna see an ugly warning message. You guys see that? Flash sims are no longer supported.
Yes.
All right, so that means that if you were to go like normal and click with this little play button, you're not going to have any success at all. It'll fail. And it's just, you know, as you said, I mean, they're no longer being supported. So what it tells you to do is it says, well, use the HTML version. So you kind of go back and look around. Down here is a little link off in the bottom right hand corner here. It says back to HTML5 or HTML5 version. Okay, you can barely see it. You can see the big triangle and everything else, right? But there's a little link here, a little inconspicuous link. You click on that, and that will give you a collision lab. Do you guys see that now? So that everything changed, this collision lab. Do you guys see that?
Yes.
Excellent. Okay, now we click that play button. So again, now we're cooking with gas. We're firing up now. So yeah, that surprised me. I usually run through these labs like the previous evening, just make sure that, you know, nothing changed, or nobody changed something behind my back. It's the nature of software, which is, I call it software entropy. You know, it says, you know, you take a piece of software that works perfectly fine, you put it down someplace, you pick it up a year later, and hey, this doesn't work. You know, so all right, so I'm going to go to the lab that, you know, I would say use the lab that was written. Now there's some differences here, so we're going to kind of walk through these differences. Hopefully people who are following will see this. So again, you see the first page of the lab. I'm going to click on intro, and that's all we're going to do here. And we go on intro, we're going to see a couple of balls that look like they're equal and opposite to each other. I'm going to make some selections here. I'm going to select, let's see, velocity. Now I'll select maybe momentum as well. Maybe kinetic energy. And now notice that the slider bar says elastic. Again, I just mentioned this a moment ago. An elastic collision is one where the energy is conserved. We assume that energy is conserved in a special situation. And as I said a moment ago, no collision is truly elastic. We can make an assumption. But to use the conservation of energy in a collision problem, you have to have knowledge, or you have to pretty much be told that the collision is elastic. Otherwise, don't feel that you have permission to use it. All right. Now, what I want to do, given that, you know, things look a little different, you know, we're being asked to, you know, put, you know, to type in masses and velocities, and all you see are masses. So if you click on more data, this checkbox, now you see more things. Now you'll see a velocity pop up, and you also see the calculation of a momentum. All right. So, and what I want to try to do also is I kind of want to move the balls back. I want to give myself as much space as possible. And I'm just gonna, the first, you know, I may have to move the balls around a little bit, but first thing I want to do, and again, there's no forces in this problem, so the velocities before and after will be constant. So the first thing I want to try to do, so okay, so let me see if I got everything right. Yeah. All right, so we're gonna try different situations. Now, one of the things that, let me go to the whiteboard again. I'm looking at the table on the bottom of page 1. We have our basic setup, and one of the things, you know, that, you know, this lab is supposed to support both college physics and university physics. So university physics is more advanced. They want you to think about the physics a little bit harder. They want you to kind of ask yourself the question, I'm doing a momentum lab. I'm a professional scientist. So I want to understand, or I'm a professional physicist per se. I mean, you guys are scientists, not necessarily physicists, but I want to come up with a lab that is going to test everything. And I would say college physics students are not, you know, that I don't think that could be expected of them. So what I try to do is I try to walk the college physics students through the lab. And so what I want to do is I want to kind of suggest what you want to put down for your masses and your initial velocities in the table. So you notice in the table there's 6 columns. And so let's kind of figure out what we want to do. Actually, I'm going to put a little more space on top here. So I'm going to say mass of A, that's what you see in the lab. And what I want to do in here is I want to specify in parentheses right underneath it, that's in kilograms. I would just write right below that in your paper, it's in kilograms. You always want to state your units. All right. The next column is mass of B. And again, you want to state that that's in kilograms. And then you want initial velocity of A, initial velocity of B, and then there's more to the table, right? So we'll say initial, I'm gonna kind of shorthand. You know what? I'm gonna really shorthand. So I don't have much space. Initial velocity of A, I'm gonna call that B sub A I. All right. It's shorthanding here. And of course, again, what it should say in the thing is initial velocity of A, right? But I mean, I don't have much space. I would write underneath that, what are the units? Meters per second. And then you have your other column, initial velocity of B. I'll call that B sub BI. Not really what it really says. But that's also going to be, I write in my pencil here, meters per second. So again, these are the 4 columns I want to concentrate on. And of course, you're going to do the experiment and fill out the other column. Now there are 6 experiments. And a lot of this lab, the mathematics is very, very easy. The lab, I think, is very clean. So it should be a very easy lab to do. But the thing is, you have to kind of understand, well, what should I do? So what I'm going to do is I'm going to imagine, number one, I'm going to let the masses be the same. So I'm going to consider a situation where the mass of A is 1.50 kilograms. The mass of B is 1.50 kilograms. And I'm going to consider them going in the same direction. I'm going to let A catch up to B. So I'm going to say that A initially is going to be positive 1.00 meters per second. I'm going to say that B is going to be slower at positive 0.50 meters per second. So B is going to be going in one direction, and then A is going to be going in the same direction, but faster. It's going to catch up to it and rear end B. All right, so they're going to be on the same way. They're going to have the same masses. What's going to happen? All right, so again, first situation, masses are equal, and they're both going to go in the same way. A is going to rear end B. 1.00 positive 0.50. The second column, I'm going to let the mass of A be bigger now than B. I'll say mass of A is now 2.00. The mass of B stays at 1.50. And I'm going to imagine here now that the initial velocities are still the same. Positive 1.00, positive 0.50. So again, they're still going in the same direction. What happens when the mass of A is bigger than the mass of B? Let's get the mass of A and B equal again for case 3. Okay, and let's imagine now that the mass of A is in one direction, 1.00, but the mass of B is the opposite direction, negative 0.50. Now, I'm gonna be very, very strict on signs, S-I-G-N-S in this lab. Momentum is a vector. As such, it has a magnitude and a direction. In one dimension, the magnitude is just the scalar number. The direction is given by the sign. So it is extremely important to make sure you're very careful with the sign. Momentum has a sign. Negative, this momentum here, let's say the momentum of B right here would be, let's see, what would that be? 0.5 times 1.5, that would be 0.75 kilograms meters per second. So the momentum of B would be positive 0.75 kilograms meters per second here, but negative right here. All right, so again, for this one, 1.5 times 0.5 is positive 0.75. Again, B times B. 1.5 times negative 0.5 is negative 0.75. Again, very important to keep track of the signs. If you don't do that, you're going to get this lab wrong. Okay. What about the fourth? What did I do in the fourth? Well, I'm going to make the mass of A bigger, call it 2.00. I'll keep the mass of B the same again, 1.50. And what I'm going to do now is I'm going to keep the velocities the same. I'm going to say that A is moving off at, say, to the right at 1.00 meters per second, and B is going the opposite direction, negative 0.50. So again, we're looking at two objects initially going in the same direction, one rear ending the other. And the second two, that's experiments 1 and 2. Experiments 3 and 4, we're looking at them colliding. They're going to coming toward each other and colliding. What happened? All right. And then what I want to consider now is I'm going to consider one of the masses much bigger than the other. So let's just say for 5, I'm going to do 1.5. And the other mass, A is 1.5. I'm going to put B all the way up to 5.00. Kind of a, some small object hitting a much bigger object. And I'm going to consider, in the first case, them moving together. So A is going to go 1.00 to the right, and B is going to go at positive 0.50 to the right. And then, of course, I'm going to consider the same masses, 1.50 and 5.00. But now I'm going to consider that the initial velocity of A is still going to be to the right at 1.00. But B is now going to be to the left at negative 0.50. And do you guys see all these numbers okay? Nothing's falling off the screen?
I can see it.
Excellent. That's what I suggest that you do. You know, so that's your initial setup. All right. And then what we want to pretty much do is figure out, well, what happened. So what's nice about this, I mean, again, you want to figure out the initial momentum of A. I mean, real easy calculation. Let's just do B. Again, B, what do? I want to find P1A, the initial momentum, P1A, just for one, whatever. Well, what would that be? That'd be 1.5 the mass times the velocity, 0.5. 1.5 is 0.5, 0.75. I mean, again, this very easy calculation, multiply the two together. All right. So, so one of the nice things is that the software does the calculation for you. I mean, it's simple enough to do, but the software actually does it for you. All right. So, let me go back to share my screen. All right, so what I'm going to do is I'm going to, you know, again, this is kind of a, it's not as nice of a, as you should see the lab again. It's not as nice of a interface as the real player. All right, so I'll tell you that right now. It's a little bit annoying to actually do this lab. So you know, you'll see in a second. So what I'm going to do is I want to. So when I click inside, so I can click inside, let's say one of these text boxes for the mass. So of course I want to click, I want the mass, I mean, and we don't use A and B anymore. I guess it's mass of 1 and mass of 2. So sorry about that. That's mass 1 and mass 2. The other lab is A and B. All right. So we're now dealing with 1 and 2 now, I guess. All right. So anyway, 1 and 2 it is. So mass 1, we'll think of 1 is A and 2 is B. Okay. So anybody listen to the lab? So I want them to be equal. And so I get this that pops up. Now there is no way to type this, at least in my laptop, there's no way that I can actually type this number in. I actually have to click on the buttons. So it's a little bit annoying. So I got to put 1.5, enter. All right. And that's what I have to do. Now, luckily, mass 2, which I'm calling B, is 1.5. So they're both the same. Now, velocity of 1 will be 1.00. That agrees with the lab. I want to change the other one to actually 0.50. I think actually it's negative. So I'm going to make it positive 0.50. So I'm going to go 0.5. Again, it's a little bit of annoying to do this, but that's what it is. So 0.5 it is. All right, now I think I have things set up. What I initially wrote for the first row, I said the mass of A is 1.50 kilograms. Okay, A, remember, is now 1. 1 is now A. The mass of B, which we now call 2, that's also 1.50 kilograms. So A, B, or 1, 2. The initial velocity of again, don't worry about the positions. I'm moving those positions around, but the next column is the velocity, and we said that the velocity of 1 is going to be 1.00. Again, positive is to the right, as usually is, and the initial velocity of 2 or B is 0.50. Now notice the next column to the right after the masses and velocities is the momentum of A, and the next column after that's the momentum of B. Again, that would be the momentum of 1 and the momentum of 2 in our new software here. So again, simple enough. If you're to try to calculate the momentum of 1 or momentum of A, it would be 1.5 times 1 or 1.5. And notice right there, 1.50 kilograms meters per second. If, on the other hand, I want to find the momentum of B or 2, it would be 1.50 the mass times 0.50 the velocity. It would be positive 0.75. So the software actually gives you, does the quick calculations for you, and that is what you put in your next two columns. So that would be the 5th and 6th columns. All right. So again, I already wrote on the board what I'd like you to do for the first 4 columns. You know, the mass of A, or we call the mass of 1 now, the mass of B, or the mass of 2, the velocity of initial velocity of A, or initial velocity of 1, and the initial velocity of B, and keep going on to the right, the momentum of, or P of A before the collision, and P of A and P of B before the collision. So again, all of these can already be filled out. I've already done for this row. I can actually write down right off the bat the values for the first 6 columns. Now, to get the values for the next 2 columns, you have to select the button. And what the button's going to do, it's going to do a conservation momentum problem for you, just like you would do in your theoretical part of the class. So let's see what happens. I select the button and I get it going. You notice that the momentum catches up, bang, the rear end collision. And you'll notice that now the momentum are different. Now it's P sub X is now 0.75 and for ball 1, and it's 1.5 for ball 2. So it looks like they actually exchanged momentum. I mean, it used to be that one had 0.75. I'm sorry. Ball 1 had 1.5 and ball 2 had 0.75. Now ball 1 has 0.75 and ball 2 is positive 1.5. So right there, you could write down from the experiment what you put in the last 2 columns. So I would put in, you know, for the, so see, column 1, 2, 3, 4, 5, 6, column 7, which is P of A after the collision, or P of 1 after the collision. I just right there, I'd look at it and say, oh, that's going to be positive 0.75. And P of B after the collision is positive 1.5. And again, I would write the units of momentum for those last 4 columns. So I'm going to go return the balls. That stops them. Let me share my screen again. Remember the units of momentum. I don't want to talk about that for a second here. The units of momentum. Remember what momentum is. Momentum is mass times velocity. What are the units of momentum? It's going to be mass is kilograms times meters per second. Now, you see a combination of kilograms, meters per second. We do not honor any particular physicist with some sort of unit. That is the unit for momentum. The unit for momentum is kilograms, meters per second. So what I would put underneath, you know, the in the momentum columns, and I would just write down, make sure everybody knew that it was just kilograms, meters per second. What's the beauty of doing that? Well, the beauty is you don't have to write it here. If I write kilograms, I can just write 1.5. And it's understood to be kilograms, because I wrote kilograms here. I can just literally write numbers here now. So I don't have to go around writing numbers or writing units everywhere. And I just have to write units once for the entire column. And when I just write a number, it's understood that that number is of that particular unit. Okay. So again, that's what I would do. So that's all this lab is about. I'll do one more here. And then I'll let you, the students, do the other 4. Okay. So let me go back and share my screen again. And I'll just kind of do one more for you. Then we'll go on to the next section lab, right? Sharing my screen. Here we go. Now, what's the next section about? Well, what I want to actually, you know what? I just did number 1. I'm going to let you do row 2. I'm going to do row 3. I mean, row 2 is just another example of going, you know, the 2 balls going in the same direction. I'm going to now do row 3. Okay, so I'm doing row 3 now. All right, so I just did row 1. Listen carefully. I'm going to let you do row 2. And I'm going to do row 3. All right, so what's row 3 about? Well, again, row 3 is about setting the masses equal to each other, which I did. I already, you know, again, I selected, I had the balls return to what their initial positions. All right, so again, row 3, if you look at the notes, row 3, both the mass of A, or mass of 1, and the mass of B, or the mass of 2 in this case, they're both 1.5, as you can see that here. Now, what we're going to do is we're going to have the mass of 1, if you look, at my notes, it's going to be 1.00 positive, but the mass of 2, or the mass of B, is not going to be positive 0.50, but now it's going to be negative. And make the momentum vector go the other direction. So again, I can't type from my keyboard, at least I don't know how. 0.5. So I have to click on the actual calculator. Boom. So now you see it's going negative 0.5, and the momenta, the corresponding initial momenta, compute for you. So again, those would be the values you'd stick in columns 5 and 6. Be sure to include the sign SIGN of the momenta. Otherwise you get it wrong. So what do? Well, we click on the button. I want to get columns 7 and 8. Now, not so fast. What I really want to do is allow there to be enough space. So I may have to kind of move the other ball back. And all I'm doing is allowing for them to have enough space where they can collide and you can kind of see it. All right. And so that's what I'm doing here. I'm just moving around. It doesn't matter. I mean, what matters here is that you can actually see the collision. The balls are going to be going at a constant velocity. So it doesn't really matter how far they travel. They're just going to travel a little bit shorter or longer distance with the same constant velocity. All right. So it's just what it is for the purpose of actually visualizing the lab. So I'm going to now click the button again. Notice that positive 1 for ball 1 is positive 1.5 kilograms per meter per second. Ball 2 is negative 0.75. Now, what's going to happen? We allow them to click, bang, they go off the other direction. Well, look at that. Ball 1 had positive 1.5 before. It now has negative 0.75. It's been turned around and it has a smaller momentum. Ball 2 initially had negative 0.75, and now it has been turned around from negative to positive, and it has a larger momentum. So again, there's kind of the same kind of exchange, but here they're actually even exchanging directions. Okay. So you would go off. I did rows 1 and 3 for you on the bottom of page 1. You would go off on your own and do rows 2, 4, 5, and 6. Is that clear?
Got it.
All right. Now, I'm turning to page 2. I mean, this cool thing here is only a 3-page lab. Page 2. Now, what's different? Well, page 2 is pretty much the same deal, except what are you doing? Well, before you had an elastic collision, what we're going to do now is we're going to slide the slider bar and make it totally inelastic. All right, so remember, so let me go to my whiteboard again. I don't have much whiteboard left. I took it up with all this stuff, but I'm going to erase these numbers, if that's okay. Let's kind of write a few other things here, so hopefully you have those numbers down, or you can rewatch the video. Okay. I want to kind of remind you, remember, an elastic collision is a collision where energy is conserved. And inelastic collision, as you can imagine, is the opposite. Is a collision where energy is not conserved. You cannot use the conservation of energy in an inelastic collision. Again, most collisions are inelastic, like a railroad car bumping into another railroad car. You know, in this case, you know, an elastic collision, the typical example would be two pool balls, you know, colliding, but again, not really truly elastic, as I said earlier. Now, you could have a totally inelastic collision. Capital letters here. A totally inelastic collision is one where, again, energy is not conserved. And the objects stick together. They stick together after the collision. Like a clay hitting, you know, some ball. They stick together. They're really inelastic. So we're setting the dial to be about as inelastic as possible to a totally inelastic collision. So what's going to happen? Well, what we're going to do, my suggestion to you is when you look at the 6 cases for the masses and the initial velocities, I would use the exact same 6 cases that you used for the first table. So again, top of page 2, the settings for the mass of A or mass of B, or 1 and 2, whatever you want to call them, I would use the exact same masses and the exact same initial velocities. I would literally just take those masses and velocities and just copy them down. I would take the mass and velocities, you know, from the first table and literally just copy them into the first 4 columns of the next table. And in fact, you could just as well copy the momenta as well, because they're going to be the same as well. So really the first 6 columns of the second table, you can just copy from the first table. All the initial masses for each of the 6 cases, all the initial masses, all the initial velocities will be the same, and all the initial momenta will be the same. The only thing you're going to have to fill out after the experiment will be what's in the last 2 columns. Is that clear?
Yes.
So let me do a couple here. You'll see things will look a little bit different. All right, so I'm going to do number 1 again. So I'm going to have both the masses be the same. Yes. Let's see here. The initial velocity will be 1.0. Initial velocity of ball 1 will be 1.0. That's right. But I'm going to change the initial velocity of ball 2 to be positive. So it'll be just 0.5. We'll turn around. And again, to allow enough space to actually see the collision, I'm going to move ball 2 back a little bit. Just so you know, you can actually see the collision happen. Now, if you notice again, you know, you have the same masses. Again, if you look at the row 1 of table 1 compared with row 1 of table 2, the first 4 columns will be the same. And in fact, if you look at the initial momentum, it'll be the same as well. Now the final momentum will be very different. So let's see what happens. They come in, they catch up, bang, they stick together. Totally inelastic collision. You notice that now they both have the same momentum. They're moving together. So you write down positive 1.13. That's what you get. So again, both ball 1 and ball 2 afterwards are going to move together at positive. They're going to move together to the right. And of course, if you did the energy calculation, they would have lost a lot of energy. Now, let me return the balls. So again, what I would say here is the right two columns of row one would just be plus 1.13 each, plus 1.13. Okay, now I return everything back to normal, back again. Again, I'm going to let you do row two. I'm going to do row three. And all that is I'm going to keep the masses the same. And the velocity now, again, I'm going to keep the initial velocity of 1 to be 1.00. I'm going to turn around the velocity of B, or velocity of 2. Again, negative 0.5. So again, the setup is exactly the same as before, but now it's totally inelastic. You notice that again, what you would write in columns 5 and 6 for the initial momenta are also the same. Now what happens though? Now of course I need to readjust, or I need to adjust the ball two's position to allow there to be enough space to witness the collision. Let's see what happens. Again, what do we think might happen? Well, ball one has more mass than ball two. So I'm kind of think that, and of course the momentum of ball one in magnitude is bigger than the initial momentum of ball two. So I'm going to think the ball one is going to win, and the two are going to go off together at a lower momentum to the right. That's what I think is going to happen from my intuition. Let's see what happens. They come in, boom, they move off very slowly to the right. They're both going at a final momentum of 0.38. So you'd write, being very careful with your signs, positive 0.38. I mean, what I would do if I was you in all of these tables is I'd be very methodical. I'd put pluses where the values are positive. I would put minuses where they're negative. I normally, you don't, if something's positive, you don't put a plus. For this lab, I would say it's better to put the plus, because you're being very, given that the SIGN sign is so important in this lab, it's very important to be I would say diligent with your signs, to the point of even writing down the plus signs. All right. So again, you would go through these other, you would go by yourself, do steps 2, 4, 5, and 6, and there you go. Now, you go down to the bottom of page 2. I mean, pretty much you're done with the actual software at this point. At the bottom of page 2, let me stop sharing. Let's go back to the whiteboard. So we're pretty much done with the software. So looking at the bottom of page 2, we call that in the lab, it's called part 2. We want to kind of analyze what we just got done seeing. All right, and so what this table really is it really wants you to copy the data that, or basically look at the total momentum, right? And so let me look at, so there's two tables. There's the elastic table and the inelastic table. So the first table is really the elasticity, and I'm looking at part 2, page 2. We have 2 tables. Elasticity equals 100%. That means totally elastic collision. The other table is elasticity. Okay. Move this to the left. All right. Elasticity. Yes, that's a word. It's equal to 100%. Elasticity equals 0%. Totally elastic collision. Totally inelastic collision. All right. So what do we do? So let me kind of just look at as examples here. So we did number 1 together. So let's go back to our data. And we want to find the total momentum before the collision, for part one. So let's see, let me go back to my table. What did I write down? Or actually, what did the software tell me? That's a nice thing. I didn't even do the calculation. All right, so before the collision, I had P1 I, and that was positive 1.5 kilograms meters per second. And P2I, what's that? That was positive 0.75. And then I look after the collision, what happened? Well, P1F, remember they exchanged momenta. I'm keeping the hats off. I mean, even though they are vectors. Positive, so it went to positive 0.75 kilograms meters per second. And this would be work that you would kind of do off on the side, turn in. P2F would be positive, and again, they exchange momentum, 1.50 kilograms meters per second. Okay, so what's this whole lab about? This whole lab is about verifying the conservation of momentum. All right, well, what's PI? Initial momentum. P1I plus P2I. Okay, well, what is that? You add the two together, you get positive 2.25 kilograms meters per second. What about P sub F? Total momentum. Remember, total momentum of the system. Total momentum of all objects in the system is what's conserved. P1F plus P2F. I add these two numbers together, and lo and behold, it is positive 2.25 kilograms meters per second. Momentum is conserved. So what would I put here is what do I put in the table? Well, so again, I just did the calculations. What goes in the table? If I have enough space here. I have the before and the after. So again, it says total momentum before. I'm just going to write before. You would want to be more explicit after. And what did I just show you? Well, I showed you was, again, what am I going to do myself a favor? What am I going to write here? So I don't have to keep on writing the units. Blah, blah, blah before. Oops, sorry. You know, whatever all this stuff says before, well, I would put, to do myself a favor, I would just put kilograms meters per second. Always, when you write a table, you do a figure. Anytime you express scientific data, you need to tell your reader what the units are. Okay, otherwise it's just a number and people don't know what you're talking about. So you got to make sure, you must make sure you state your units. That's true for your chemistry classes or any other science class. After. Again, do yourself a favor, kilograms meters per second. If I don't do it here, then I'm going to have to repeat every single time I write my number and write those down. I mean, that would be ridiculous. Just do it one time. And so what did we just go ahead and calculate? Well, we just showed that in both cases is 2.25. And that's what we tried to show. And if you go to 3, do the exact same calculations, go through the exact same thing, math that I just got done doing, what would I write here? Well, I would show in 3 that the total momentum before the collision was 0.75 and the total momentum after the collision was 0.75. Again, I would do the exact same math that I did before, that I did here. For the inelastic case, what I found before, I mean, again, the before is going to be the same thing. It's the same setup, right? So before kilograms meters per second, after kilograms meters per second, no surprise, in case one, we have again positive 2.25. It's the exact same setup. If you look, if you calculate carefully for the numbers we had, afterwards we have positive 2.26 with a little bit of error. And for case 3, you go through all the numbers we went through, you would see that before, this is what I got, positive 0.75 before, just like before, no surprise. But afterwards, there's a little bit of error, positive 0.76, so on and so forth. But, you know, to within experimental error, certainly you see that momentum is conserved. And again, what is conserved? It is the total momentum is what's conserved, not the momentum of any individual object. All right. So again, that's very important. That is one of, you know, again, that's what's part of the queries. You know, it's really important to understand this. If you go to the very, very last page of the lab, query 5 says, if the momentum of a system is conserved, is the momentum of each particle in the system necessarily conserved? The answer is no. No way, right? Because as we saw, the total momentum, again, what we're seeing here, I'm sorry, it's erase a little bit here. What we're seeing here is the total momentum of all the objects in the system. 2 objects is what's conserved, not the object of an individual, not the momentum of an individual object. It is the total momentum. I add up all the momentum of a system, an isolated system before, it's at any time afterwards, the sum of all the momenta will be the same. That's what's conserved. So if I look at query 5, for instance, very important to understand this. And some people, when they don't understand momentum, they'll say, well, momentum of ball 1 is conserved before and after. No way, it changes. So again, you know, if you look at query 5, I just want to really nail this down. Get the last page lab. The momentum, the conservation of momentum states that in an isolated system, the total momentum of all objects in the system at time t1 is the same as the total momentum of all objects in the system at a later time t2. Now this could be after a collision. I'm just trying to be very general. I'm not even mentioning collision. You know, it could be I'm just watching the particles do their thing and I calculate the momentum. I mean, again, if it's an isolated system, every time I calculate the total momentum of all the objects in it, it'll be the same as when I later calculate the total momentum. Again, the momentum, the conservation momentum is a system concept. It is not an individual concept. So to continue with query 5, I would say, I mean, again, you know, some students don't get this, but the conservation of momentum does not say that the momentum of any individual object is conserved. And that's not what it says. Okay, so again, that's something that some students, have to think about a little bit. But again, it's a system concept. Okay, I just wanted to really nail down query 5. All right, so you will effectively, when you get done doing all the other, I did trials 1 and 3 for you for both the elastic and inelastic cases, and again, we were ready to put numbers down for part 2. Well, when you get done doing trials 2, 4, 5, and 6, you'll be able to fill out those corresponding rows in the 2 tables in part 2. And earlier, you're just looking to see is the momentum, so total momentum of your system before the collision and the total momentum of your system after the collision. That'll allow you to complete the tables on the bottom of page 2. Okay, I'm on page 3. I was briefly on page 4 there with query 5, but I'm on page 3. So summarize in a few sentences what you conclude about this data. I mean, really, in both the elastic and inelastic collisions, momentum is conserved. You can definitely say that. I mean, again, you have to do the data yourself, but what the data tells you is that in both inelastic and elastic collisions, momentum is conserved. I mean, that's what I say. All right, now we go to the queries. What do we mean to say that momentum is conserved? Again, I've gone over a lot of stuff here with you, so I'm going to let you answer that question. What does it mean? Well, okay, I'll tell you what it means. It means that, again, what I just got done saying, if you add up all the momenta of all objects before collision, right? What I just wrote down, at some time t1, the total momenta of all the objects after collision is the same at a later time t2. Again, the answer to query 1 is very similar to the answer to query 2. But that's what the conservation momentum is exactly that. Now, be very careful. What is conserved? What's conserved is the total momentum. What's conserved is a vector. When you add up all the momentum, you actually get a resultant vector. Okay, so when you add up all the momentum of the system beforehand, you'll get a momentum vector. And then later on, maybe after a collision, you add up all the momentum afterwards, you should get the same momentum vector. Conservation momentum should be equally true in each coordinate. So if you have an x coordinate, y coordinate, and z coordinate, you should be able to apply the conservation momentum in x and y and in z independently. And all together, what is conserved is an overall resultant vector. Number 2, query 2, what's the difference between an inelastic and an elastic collision? And I've said this a few times already. The elastic collision, in elastic collision, energy is conserved. You can apply the conservation of energy. In an inelastic collision, energy is not conserved. Again, I wrote this out in great detail a few frames ago. So again, look back in the video. I answered query 2 very with great detail. What are the units of momentum? Can somebody answer that? What are the units of momentum? Query 3.
Is that the kilograms meter per second?
Absolutely right. Absolutely right. All you have to write down for query 3, units of momentum, kilograms, meters per second. And again, we do not honor any special physicists with it. Those are the units. Very good. Query 4. Let me ask you this, guys, for the You guys listening? Under what condition is momentum conserved in the system? Under what condition is momentum conserved in the system? What's the only restriction you have for momentum conservation? Remember? Anybody? So for query 4, it's very important. When you apply a law or a principle, you have to know what are the restrictions for you to apply such a law. And the conservation of momentum applies to isolated systems. i.e., systems where the external force on it is 0. Again, I did not say that there's no forces on it. It's just that whatever external forces, again, external forces to the system, whatever forces, they have to sum up to 0, the 0 vector. And that's query 4. Query 5, I talked about query 5. So that's really all I have. You want to stick around? Yes, Chidera took off. All right. So hopefully he'll see the video. I wanted to address the conservation of energy lab. He said, Chidera said that that lab has problems. Let's go take a look at that real quick. So give me a moment here. I'm just gonna, so this lab, I guess before I go on, anybody have questions about the conservation momentum lab?
I'm good.
Okay, let me fire up. So this is gonna take me a minute here. I'm gonna bring down the Word document for conservation of momentum. Okay, let me bring down that system or that software. All right, I'm just gonna take a look here. So like I'm bringing up, so you don't see what I'm doing right now, but I'm bringing up the conservation of energy Word document that I have on my computer. Because what surprises me is we went through that together. I didn't have any problems.
Yeah, I think they did like an update or something, because I was trying to go back through it today and it wouldn't let me get into what we went through over last class.
Oh, you know what? Oh, goodness. I think I had to do all kinds of stuff with a jar file, a Java file once upon a time. I may have to actually do that data for you. That's okay. Let me see. I may not have. I went through a whole. Yeah, it's unfortunate. All right, let's see.
Yeah, Professor, this is Ivan.
Hi, Ivan.
I also had an issue with downloading that file from the lab you're looking at right now, the one that's due to do today. And every time I try to open it, and yeah, that one, every time I try to open it, it just basically told me that I didn't have permission because it was some weird, it was like it wasn't an identifiable source. And so I had to do so many updates. I had to download Java, and then my computer completely crashed. And so I had no way of looking at that lab at all.
I'm sorry. Well, let's see if I have the same lack of success. So let me share my screen. I brought it up. All right, so anybody who's watching this video, let's see. Now I can make the due date a little bit later. All right, so what I normally would do when I did last time, do you guys see the energy skate park?
Yes.
All right, let me see if I have the same issues you guys have. Now, we may have to go to the HTML version, but I don't. Okay, so what I have here, I have a little message here. I say keep. And it should take a moment. Open window. I think it's succeeding. But it might have been that I did some preliminary Java work to make this happen. What I could do is just scan and send my my data. You know, something to go, something to go by. So I think I'll just do that. Because if you guys are having problems and you guys are pretty good at labs, I'm sure some of the other students will have problems too. Hang on, we're still thinking. All right, I'm seeing something. It's thinking. Hypnotized here for this thing. You guys see this scroll bar going back and forth?
I can't see it.
Okay.
Yeah,
All
I
right.
got nothing.
Now, okay, so let's see, update now, I guess. Do you see the skater going back and forth?
No.
All right, so let me, so I probably am sharing the wrong thing. Okay, so I have it up. Let me go back. Let me stop sharing the previous screen. I'm not really sure what you guys are seeing. Let me share something else. I'll try to share the skater. All right, so it very likely is that there's a, all right, so you should see the skater going back and forth. You guys see that?
Not yet.
Wow, okay,
Now, yeah.
excellent, okay. So that's just the Zoom delay. All right, so I have to harken back when I first did this lab this last summer. Yeah, I one of the labs I had difficulty with a Java file, and I think I actually had the professors at the University of Colorado for one of these labs, and they kind of walked me through what to do. So I had difficulty too, to the point where I had the walkthrough. So I guess I forgot about the difficulty. I probably should make a note of that. So what I'll do is I'll send my data out. I'll do that tonight. Hopefully that's enough time for you guys to finish the write-up. All right. Anything else? I'll do that. I'm gonna go to dinner here pretty soon. So when I get back, I'll do that. So I'll probably be later tonight.
Okay, and is the lab still due tonight, or can we push it till tomorrow night?
Oh yeah. You know what? Yeah, very good. Today is Friday, isn't it? Push it to next week. Next Friday.
Okay, thank you, sir.
Yeah. It's not your fault that the software's messed up. So yeah, so that's fine. You'll just have 2 labs to turn in next Friday. I will send an email out to everybody. So yeah, so anybody who sees this video, but again, I'll
Awesome.
send.
All right, thank you.
All right, you betcha.
Yeah, thank you.
So you won't get that email for a few hours. So any other questions?
No, I'm good. Thanks.
Excellent.
I'm
All
good
right.
too. Thank you.
You betcha. Have a good night.
you do the same.